Okay, this is hypothesis testing, scenario 3. So a credit card company wondered whether giving frequent flyer miles for every purchase would increase card usage. That's probably important. Which has a current mean of 2,500. They gave free miles to a simple random sample of 36 credit card customers and found the 36 is probably important, and found the sample mean to be 2,542. Assume the population standard deviation is 109. Okay, so what do we have? What is our initial claim? What is the status quo? What have things been over time? In the long run, what have things measured? Well, the amount of credit card usage, which is what we're interested in, has been over time about $2,500 a year. 2,000, oops, mu equals $2,500. The alternative is going to be mu, and it's also going to be $2,500. But they're wondering what? Well, they wonder if it's increased, so they wondered if it's gotten greater. All right. Once again, the mu is the same. This is the same. We just have to figure out our inequality, and the null hypothesis is always going to be equal every single time. So, what is our parameter? So this is number one. Our parameter. Let mu equal the true population mean card usage. Probably should be card usage in dollars, but we're going to try to keep it short and just call it mu equal the true population mean card usage. All right. Number three, that's conditions, and we're going to assume that they are done for this class. Number four, write the equation. Z equals x bar minus mu sigma divided by the square root of n. Number five, we don't have data, so we don't, number five says draw the graph and shade. So if I'm drawing the graph, over time it's been 2,500, that's the mean, and we're always centered on the mean. But then we got a sample value that was above it, that was 2542, so we can shade up and to the right. This is going to positive infinity, all right? So we want to know the likelihood that we get something this extreme, or basically $42 more by random chance. Did this happen by random chance? Or do we have enough evidence to say, you know what, the frequent flyer miles actually helped and we are using the card more often? The next thing says enter the data. We don't have data to enter, so that's good. The next thing says plug values into the, we need to list our values. What are our values? Well, the mean was 2,500. The standard deviation was 109. The X bar equals 2542. And they had a sample of size 36. So number 8, we're going to go ahead and plug into that. So we're going to have the probability that Z, which way did our alternative is greater than, all right, greater than 2542 minus the 2,500. That's my X bar, that's my mean, over my standard deviation of 109, divided by the square root of 36. Now I'm going to go ahead and calculate this. So I'm going to go to stat, arrow over to test, z-test, press enter. Well, our claim was 2,500 because that's what the status quo, that's what it's been forever. Our population mean is 109, 2542 sample size of 36, and our alternative hypothesis was a greater than. And when we look at our graph, we shaded up to the right. So when I did that, I end up getting the probability that Z, this is number 9, probability that Z is greater than 2.3119, and that equals 0.0103. So this is my p-value. All right, and I'm going to run that one more time really quickly. Stat test, so y'all can see where it came from. Z-test. 2,500 was my mean. My standard deviation is 109, 2542, 36 is my sample size. And I had a greater than. I press calculate. And I get the probability that Z is greater than 2.3119 equals 0.0103. And that P is my p-value. All right. Now, they did not give us a alpha level, but this time I'm going to use an alpha level of 0.01. All right. Well, that's greater than 0.01. If I make them the same length, 103 is bigger than 100. So if I use an alpha of 0.01, what happens? I fail to reject. All right. So our conclusion. Our p-value is 0.0103. We fail to reject the null. There is not sufficient evidence at alpha equal 0.01 to suggest that the true population mean card usage is greater than $2,500. All right, the next thing. So basically our p-value, but that's because we chose an alpha of 0.01. What if we'd chosen an alpha of 0.05? Well, once again, our p-value in our alpha. Had we chosen 0.05 instead of 0.01, this was our p-value, 0.0103. I didn't change that, but I changed our alpha to 0.05. So I'm going to make these the same length. Well, 500 is clearly larger. So in this case, my decision would be if the p-value is less, we reject. So up here, we failed to reject. Here, we're actually going to reject. So my new conclusion would look like this. We reject the null. There is sufficient evidence at alpha equal 0.05 to suggest that the true population mean card usage is greater than $2,500. So real quickly, just by having a different alpha level, sometimes we'll reject versus fail to reject, because our p-value was the same regardless, but what did change was our alpha level. Now, we, as good statisticians, we should take the alpha level, choose an alpha level before we run the test. So in this case, we wouldn't have done this. If we'd chosen a 0.01, we say, nope, it didn't, it's not good enough. But very likely some business person says, yeah, but if you'd use 0.05, you'd say there's a difference. So what's this? What are we saying here? Here we're saying there's basically a 1% chance that we'd get a test statistics as extreme as 2542, if in fact there's still $2,500. We're saying the same thing here. The only difference is we're willing to have an error rate of 5%. All right, because that's our alpha level. All right, that concludes hypothesis testing. Please make sure you always follow the recipe card completely.